Hi all, welcome back to Capacitor and Dielectrics Part 2. Today we're going to see capacitor connected in series and parallel. Figure above shows three capacitors connected in series to a battery of voltage V. Electrons flow from negative terminal of the battery to the plate C3 and charge it negative Q. This negative charge induces a charge positive Q on the other plate of C3 because electrons on one plate of C3 are repelled to the plate of C2. Hence, this plate is charged negative Q, which induces a charge positive Q on the other plate of C2. This in turn produces a charge negative Q on one plate of C1 and a charge of positive Q on the other plate of capacitor C1. Hence, the charges on all the three capacitors are the same Q. So, capacitors connected in series where the total charge Q equals to Q1 equals to Q2 equals to Q3. Of course, you can connect more than 3 capacitors in this circuit. It's up to you whether you want to put 3 or more. But the charge in each capacitor will remain same no matter how many capacitors are in the circuit. Whereas for potential difference across each capacitor are not same, V1 is not equals to V2 and not equals to V3. So, V1 not equals to V2 not equals to V3 for the situation where C1 not equals to C2 not equals to C3. If C1, C2, C3 are identical capacitors, then the V1, V2, V3 will remain same, where V1, V2, V3 will give the same potential difference across C1, C2 and C3. Generally, the potential difference across capacitors C1, C2, C3 for series connection are V1, V2 and V3, where V1 is equals to Q1 over C1, V2 which is equals to Q2 over C2 and V3 which is equals to Q3 over C3. It is crystal clear that the charge remains same across capacitor C1, C2 and C3. So the amount of the charge in capacitor C1, capacitor C2 and capacitor C3 will be Q. The total potential difference across A and B, VAB, is equals to V1 plus V2 plus V3. So for the total potential difference, you're going to add up all the potential difference across capacitor C1, capacitor C2 and capacitor C3. If you have more than 3 capacitors, then you're going to do the same process by adding positive V4 or V5 till the infinity. You're going to substitute all the V1, V2, V3 accordingly into this equation, where C equivalent is Q over V, or we call it total capacitance in the circuit is Q over V. Therefore, the equivalent factory capacitance C equivalent for n capacitors connected in series is given by 1 over C1 plus 1 over C2 plus 1 over C3, all in reciprocal shape. So, all the 3 capacitors already combined to one capacitors, we call it C equivalent. How about if the 3 capacitors are connected in parallel? When 3 capacitors are connected in parallel to a battery, the capacitors are all charged until the potential differences across the capacitors are the same. The potential difference across each capacitor is the same as the supply voltage V. Thus, the total potential difference V on the equivalent capacitor is V equals to V1 equals to V2 equals to V3. For capacitors are connected in parallel, Q1, Q2, Q3 are not same. But the potential difference across each capacitor is the same as the voltage supply V. So the charge on each capacitor is Q1, which is equals to C1 times V1, Q2, which is equals to C2 times V2, and Q3, which is equals to C3 times V3. And the potential difference V1, V2, V3 will remain same as the supply voltage V. Now the total charge in the circuit is equals to Q1 plus Q2 plus Q3. Mathematically, we substitute all the Q1, Q2, Q3 with C1V, C2V and C3V, where the potential difference across each capacitor will remain same as the supply voltage V. Therefore, the equivalent effective capacitance C equivalent for n capacitors connected in parallel is given by C1 plus C2 plus C3. So these are the three capacitors which is combined as one C equivalent in this circuit, where the potential difference across AB is V. Let us see a few examples of capacitors in series and parallel. However, this example 1 in the circuit shown above, calculate the charge on each capacitor, and B, equivalent capacitance. For the beginning part, you have to identify whether the two capacitors are in series or parallel. Please take note that you must be able to differentiate between capacitors that are connected in series from capacitors that are connected in parallel. Capacitors are in series if the plate of one capacitor that is charged positive is connected to the plate that is charged negative in the second capacitor, and so on. So these two capacitors are connected in series. Capacitors are in parallel if the plates that are charged positive for all the capacitors are connected to one point X, and the plates that are charged negative are all connected to another point Y. Exactly like this. Whatever by these two T junctions, which is separated these two capacitors, therefore they are connected in parallel. So after the short notes, I don't think so you got problem in identify these two capacitors whether in series or parallel. Definitely these two capacitors are in parallel because differ by these junctions, which is separated these two capacitors. So they are in parallel. The two capacitors in parallel, the potential difference across each capacitor is the same as the voltage supply V, which is equals to 50 volt. So charge on each capacitor Q1 is equals to C1 V1, Q2 which is equals to C2 V2. We can substitute all the possible values into this equation to get the charge on Q1 is 50 microcoulomb and Q2 is 100 microcoulomb. Simple like a bubble without giving you any trouble. For section B, equivalent capacitance for parallel circuit, we have to add in C1 C2 together to get the equivalent capacitance as 3 microfarad. Let us see another example, example 2 in the circuit shown below. Let us see another example where the two capacitors are connected in series. Connections are in series because there is no junction at all in the circuit, like what we have seen in example 1. So the equivalent capacitance will be in reciprocal shape, where we have to substitute all the possible values in this equation to get the C equivalent as 6.67 times 10 to the power of negative 7 farad. For section B, charge on each capacitor. For two capacitors in series, they have the same amount of charge carried by each capacitor. So Q1 and Q2 is the total amount of the charge in the circuit as Q, where C equivalent is equals to total charge in the circuit per unit total potential difference in the circuit, where the total potential difference in the circuit is 50 volt. Therefore, the charge on each capacitor is equals to 3.34 times 10 to the power of negative 5 coulomb. which is equals to total amount of the charge in the circuit SQ. For section C, calculate the potential difference across each capacitor. Potential difference across 1 microfarad is equals to Q1 over C1, which is equals to 33.4 volt. For the potential difference across capacitor 2 microfarad, we have to take the total potential difference across 2 capacitor, which is 50 volt, minus the potential difference across 1 microfarad, which is 33.4 volt. Then you will be able to get the potential difference across capacitor 2 microfarad, which is 16.6 volt. Simple like a bubble without giving you any trouble. Let us see another example, example 3. In the circuit shown, calculate the equivalent capacitance, charge on each capacitor, and the potential difference across each capacitor. To find the equivalent capacitance in the circuit, I have to simplify this circuit into this form. C2 and C3 are in parallel. We combine these two to C23 and it will be 12 microfarad. And now these two capacitors are in series. They are in reciprocal shape, where the C equivalent is 4.0 microfarad. For section B, charge on each capacitor. Junction exists between C2 and C3. You can see one junction here. So C2, C3 are in parallel, where these two capacitors have different charge or amount of the charge. Capacitor C1 will carry the total amount of the charge, which is equals to Q1. It breaks here as Q2 and Q3. We assume that total charge entering and leaving these two junctions are remain same, and the amount of the charge for capacitor C2 is Q2 and capacitor C3 is Q3, and the potential difference across C1 is V1, and across C2 and C3 will remain same, where V2 equals to V3, because these two capacitors are in parallel. The total amount of the charge, which is equals to Q1, equals to C equivalent times total potential difference in the circuit, which is equals to 12 volt, which is equals to 4.8 times 10 to the power of negative 5 coulomb. Once we get the total charge or amount of the charge for C1, which is Q1, we can find the potential difference across C1, which is 8.0 volt. So the potential difference across C1 is V1, which is equals to 8.0 volt. When we take 12 volt minus V1, we will get V2. So at 12 volt minus 8 volt is equals to 4 volt. V1 is 8 volt. V2 is 4.0 volt. It means capacitor 2 and capacitor 3 will have same potential difference across it, which is equals to 4.0 volt. The potential difference across C2 and the potential difference across C3 is 4.0 volt, where V2 equals to V3, which is equals to 4.0 volt. Once we settle all the technical parts in the circuit, then you can answer easily section B and section C. For section B, charge on each capacitor. Q2 is equals to C2 times V2 and Q3 is equals to C3 times V3. V2 and V3 is equals to 4 volt, 4.0 volt. Hence the charge on Q2 is 1.6 times 10 to the power negative 5 coulomb, and charge for Q3 is 3.2 times 10 to the power negative 5 coulomb. Simple like a bubble without giving you any trouble. And finally section C, the potential difference across each capacitor. For C1 is 8.0 volt and for C2 and C3 is 4.0 volt. Thank you for watching this video. Thanks a lot and thank you to the Lord.